Please write down the name.
Okay, hello everyone, I'm the reporter from Maxwell, and today I will talk about the problem number 15, welding flow. For the problem statement, we can see that when we strike a ball with some water and the water is moving in the ball, we can hear the characteristic sound called whirling. So we need to investigate and explain the phenomenon. For the whirling of the statement, investigate are going to be the striking energy and the geometry shape of the ball and the water and the ball vibration mode. And I change the type of the ball, the movement of the water, and the depth of the water as parameter in my experiment. And I will mainly focus on the definition of the whirling and the phase of sound change. Okay, so let's define the whirling sound, and I will focus on the analysis of the sound change and the comparison of the ball of the condition, and we will expecting that the frequency will change. And this part, I will mainly focus on the geometry shape of the ball, and is considered to, and it needs to consider by the whirling sound. And let's talk about the experiment setup. I use two different types of ball, and the first one is made out of stainless steel, and the second ball is made out of bronze. And to compare the two conditions, I use FFT, phase Fourier transform, and STFT, short time Fourier transform, to do the acoustic analysis. And we can see that the difference from the spectrum, the without water and with water condition. I use a rope, use a cotton rope to hang the ball and make it to do the pendulum. And in a without water condition, I also do the analysis. And we can see that the dominant frequency is different, since the ball's geometry shape is different and the material is different. And with water condition, we can also see the ball A's FFT spectrum is more complicated, and the ball B is the second dominant frequency's amplitude is decreased. And for the third condition, with water and shaking, we can find the dominant frequency at the ball A and get the characteristic frequency at the ball B. And we also observe the acceleration frequency at the STFT. And we assume that this is the meaning of the whirling feature in STFT. And we assume that the sending wave considered in the ball when we strike the ball, and the sending wave's energy can be considered as the kinetic energy and the potential energy. And the coefficient of kinetic energy can be presented by the A, and the potential energy can be presented by B. So we get B divided by A, get the square angular of the frequency, and also known the frequency. And for the wine glass theory, we can know that they also consider the kinetic energy and the elastic energy, and also the function of liquid shape about the frequency. And to simplify it, the theory get this formula. And since the formula is simple, we can also fit the experiment data to this theory. So this is my experiment data and fit with the theory, we can get that the n is means by n is means by the coefficient of the shape, and we get our experiment data. The n is equal to 4.77, and the theory data, the cylindrical glass, the n is from 3 to 5, and this represent that our experiment can apply to the theory. So I will do the further experiment and do more research about this theory and further more complicated theory. To compare the stripe at different phases, we can see that the icon is meant by the condition of the water in the bowl, and we can see that there's difference between the STFT spectrum, and we also overlay the FFT spectrum and can see the frequency shift in different phases of surface. This is because the geometry shape of the bowl and the water will be influence the whirling feature. And I also do the comparison between the strike at different forces. The first one, you can even hear the sound because I strike really small force. And the second one, we can hear the characteristic sound whirling and also see the STFT spectrum and the acceleration frequency. And this is because the energy I strike the ball need to be considered by the whirling spectrum. And the strike position, I also do the strike position to compare it. I strike the side of the ball, the up and the down, and we can see the frequency value is not changed, and the same phenomena is appear in the still water, and the second condition and the third condition, moving the water. The whirling feature, we can see it in STFT spectrum, and we also get the relationship between the resonant frequency and the depth of water contained in the bowl, and I strike the bowl. And I fix the formula because the water move condition, the statement condition, will hear the whirling sound and get the STFT spectrum. So I do the exponential, I add the exponential and consider the time dependence. And we assume that varying water shape causes the oscillation frequency and strike position does not affect the dominant frequency. In our theory, to compare the vibration mode to the frequency, I assume that I strike the ball and the ring of the I strike the side of the ball, and the ring of the ball will have the standing wave. So the standing wave appearance can be seen at the side. And how to know the vibration mode? The theory, the author in the theory use the holographic interferometric to see the vibration mode in this experiment. And he also considered the kinetic energy and elastic bending wave, the material factor, and the shape of factor. And I also fit our experiment data to the formula. And the second formula is the field water in the bowl, and can be seen the frequency change. And the third formula is consider the vibration mode to the frequency. And we get the fit about the coupling, the coefficient of coupling in the second formula, the alpha. Our experiment is 1.955. It means that the bowl and the water coupling is invented and be considered the welding feature. So I also do the console simulation during the theory is to get the vibration mode to correspond it to the frequency, the higher vibration mode. And for example, I do the ball A and fill with 10% water, and I shake it and we'll hear the characteristic sound as we previous here, and we can get the experiment and the console simulation value is simulated and get the value and the multiple vibration mode and get this correspond the vibration mode to the frequency. And I also do a lot of experiments by change the parameters, the type of ball, and the audio of type B is dirtier than the ball A, so I use the ball A to do the further experiments. Because I need to distinguish the noise and the welding, the actual welding sound. And the depth of water and the way of I move, linear and circular, and the angular of the ball. Thanks, everyone.
Okay, I have some questions to ask you. Did you think that it's the ball or the water or the air that vibrates will cause the welding sound? Which one? The ball vibrating, the water, or the air? The air that's vibrating that causes the sound.
I think that the ball and the water coupling will
The
be
water coupling?
yes.
Can you elaborate more on what's coupling here?
And the water, the coupling means the vibration mode is not only the
Whose vibration? Water.
Sorry, the vibration sound.
The vibration sound.
Yes, the sound when we strike the ball, the sound is not only considered the ball, but only the
Okay, I would like to talk about this later.
Okay.
Can you please turn to page 25?
25.
25. Yeah, what's that F04? Who's F0? Like like this is.
This is the resonant frequency. The balls with no water. Yes.
The balls with no water.
Yes, it's a fundamental equation.
Okay, and I think I see you mentioned a standing wave in your experiment, right?
Yes.
And I also see that you use string to suspend your ball in the air. Will the string affect how the ball vibrates? Because since there's standing wave there, will that, if the point is not at the node, will that affect how the ball vibrates?
The welding sound only.
No, I mean the standing wave you consider here.
Eh.
Yeah, because the standing wave you consider here will be affected by the ball. But the ball is suspended from the spring, means that the point be suspended cannot vibrate as much as that with those without suspending. You know what I mean? Okay, I mentioned it later. honorable judges and fellow contestants. This is the opponent speaking, and I am going to oppose problem number 15, wailing ball. This is a problem statement and a reporter focusing on the sound change, the program analysis, and the conditions of the ball. This is the summary of the report. The phenomenon is that the frequency change when the metal ball is struck, like you will release a wailing sound. The theory they use is striking energy, and the geometry of shape, ball, water will influence the frequency. And the standing wave, kinetic energy, potential energy is also considered in their theory. As for the experiment, they do a resonance frequency, and they also do console simulation. They also consider how that of the water will affect the sound of the wave. There are some pros and cons about the reporter's reporting. For the pros con, they provide a wide range of parameters discussed and a detailed console simulation, and also considering standing wave in part of the series. As for the cons part, they should also consider background noise as well, because like when you track your sound, it is not always silent, and the experiment setup is unclear. How did you hit the ball by hand? The force is controlled. Is it tilt? And in page 17, how do you define small or big large force? And what's the smallest force required? That means you need to provide more boundary conditions in your series. And in page 20, like I mentioned before, how do you control the degree of tilt since you suspended the ball in the air? Here's some discussion I would like to discuss with the reporter later. As for the theory part, you mentioned the definition of wailing, but I didn't see something that is elaborating on that. And the ball's water distribution's geometry, which is the major part that will influence the sound. You didn't mention that. And the equation, I have something to talk about with the equation you provided earlier in your PPT. And about the natural frequency, I'm not sure whether you use it or you just don't know what that is. And as for the phenomenon part, the boundary conditions and the degree of tilt I have mentioned in the pros and cons. But here I want to reiterate again, not every time you strike the ball will move in the same way. Meaning that the water and the ball's geometry will not be the same. So you cannot compare that to in your experiment. As for the others part, the bottom of the ball is not flat. So if you want to consider a cylindrical-like ball, you cannot use that ball in your experiment. And as for the problem statement, it mentions that there is a characteristic sound. I would like to ask, what character do you think that is? And as for the ball, water, air contribute to the sound, which is the major part. So I would now like to invite the reporter to answer some of the questions. So how to do, first I would like to ask, how to do control the tilt, the degree when you suspend your ball inside on the air. There will be tilt, right? Have you ever calculated it?
Yes, it's a parameter I do. And most of my experiment, I didn't.
Can you please show me?
Okay. Most of my experiment, I didn't hand it at the air.
I mean, like some experiment you did.
Right. And for the consider the angle, I use a rope and I use a kit to measure the angle.
How to measure the angle? Like you have a ball here and you cannot see the water distribution inside. So how do you going to calculate that? Like
yes.
The ball is not transparent. So how?
And before I strike the ball, I pull the ball and ensure that it's
you
my
use hand, right? So
yes.
is there an initial velocity there? And that initial velocity is not always the same, right?
Yes.
So
it's
that's
the angle.
deviation.
Yes,
so
I consider the angle.
No, I mean like, can you please play this video again? Like when you release the ball here, you put an initial velocity to the ball, and that initial velocity is not always the same. This means that in every data you collected, there must be some deviation there. So instead of using hand to release this ball, I will suggest you to put it on the table and use the oscillator there and rotate in a circular motion, instead of just put it down, and you need to consider a lot of things there. So it's too complicated and will cause a lot of deviation.
Yes, it's
And
one of the experiments. I do the rotation to strike the ball, and you can be seen that I do the circular.
No, this is didn't suspended in the air. I want that like you're held in the air. Like this one. I want
Yes.
that this one.
Since it's an observation of I
It's
show-
only use observation, so
Yes,
it didn't
because
put
most
this
of-
in the experiment data. Is that right? You
Uh,
only use this to observe some phenomenon.
Yes.
Oh, okay. Then
does
that's
it
the
make
next question. Like what character do you mean in the problem statement? Can you please turn to the problem statement page? So what characteristics sound? What character is this? Did you think, in your opinion?
I think that the wailing sound is the acceleration of the frequency.
So you think that this characteristic is the wailing sound? So can you please turn to the next page about the definition of wailing sound? Give next. Yeah. So what is the definition of wailing? Which part? Like you here say definition of wailing, which is the definition of the wailing.
Okay. The wailing has a feature that
No, I mean
influence.
definition. I
Oh.
don't mean the phenomenon. I mean definition, like you mentioned. Definition of wailing. So
I
what's the
didn't write the definition of wailing
Oh.
in this slide,
Oh,
but
oh,
I
So then what's this?
it's the former slide I
Also,
describe it.
so can you describe what's wailing?
Yes, wailing is the acceleration frequency we hear and is seen in the STFC spectrum.
Okay. So as I asked before, which part, the air, the ball, or the water, which contributes the most that you hear the sound?
The water.
Contributes the most. You
In my-
mentioned that it couples, right?
Yes,
So which one is the most? Which dominant part is it?
water, because
Water.
in my experiment I do the swing without water and with water. We can know that the shaking and with none of the water, you will not have the wailing sound and cannot be see the acceleration frequency in the STFT.
So you think that without water there won't be wailing sound.
Yes,
So and only with water, like this with water is still water, like you just put it and.
the without water and with water have the same initial condition to swing like a pendulum. The ball swing like a pendulum. So we can see the video.
No.
Sorry.
I think you didn't understand what I want to ask. Let me rephrase it. I mean that there is water inside the ball. Then you hit it with different water mass inside the ball. You get different sound, right?
It's not the exactly mass.
The water mass only, like I put 200 millimeters in the same ball and another 250 millimeters in the same ball, and I hit it. I get different sound, right?
It's not the feature of the
No,
mass.
I
Is
mean
not the
different
feature.
or same.
It's different.
Like difference. So who contributes to this difference? I'm not going to tell. This is about the background sound, the noise. But I want to ask who contributes to the shift of the frequency, like you mentioned.
I think that add water and the water will can be seen the wailing.
So you see the water. Okay, can you please turn to the page that you developed on, like that? The equations like the kinetic energy and potential energy, like. Oh no, like never mind.
The number of
equation. Like 12 up, down, back. Oh yeah. So what's theta? Like representation.
The theta is the radius of the ball and is it is calculated by the number of the standing wave.
Oh, so
And as a circle has 360 degrees, and it can be divided by the number of the.
So you integrate that or?
It's a assumption and sorry, and this is the previous theory, and you need to know.
And how about this equation? What's each x squared? Like,
as we can see, for example, the kinetic energy is equal to this.
Yeah, this is the kinetic energy, and what?
A is the coefficient of kinetic energy.
A is the coefficient of kinetic energy.
Yes.
And C is the.
B is the potential energy, the coefficient of potential energy.
So why you divided this to you get the omega?
Because the square of omega is equal to.
Yeah. How do you derive this? Like you put it in, like by what you can say that. Like you put an arrow here. Like what's the previous equation that you can say that? Because I didn't see any relationship between these.
For example, you can get the relationship.
Oh yeah, how? Like can you derive it in the blackboard?
Okay. So as the equation in the slide, we can see that the kinetic energy is equal to this, and the potential energy is equal to this. So we can get this divided.
Yeah, then where's the?
And now we can get the potential energy over the kinetic energy, and we can get the N over K. The K over N is equal to.
Yeah. How come omega squared? Like here K, here N, then omega squared.
Since we fix the ball and we strike the ball, side of the ball, and the.
So you think like this is a spring-like system, like this. With the string you have like this. So are you gonna make this DC?
Yes, the side of a ball with no water, and I strike it, the deformation of the ring will do a simple harmonic
So
motion.
instead of considering this much and using theta, I would suggest you to use a metric. Like you can use mass, the metric, and your the acceleration equals to the k you mentioned here, right? And the displacement. So you can have this equation where k and m is metric, and you can through the finite element method. You can know that the x here can be written in this form, and where you can know that the omega squared is actually have something to do with its eigenvalue. You know what's eigenvalue? Okay, so it has something to do with eigenvalue. So if you use this equation, you derive it like using this way. Will it be too simplified? Like you use theta here. So because you also mentioned the geometry of the water, right? The distribution of water and right?
Yes.
That will change. Right? So you can just include it in this matrix, in the matrix of the math. So you don't have to consider that much for the theta, or you have integrating something or a and b. So why don't you just use matrix to symbolize the distribution of the water? Okay, that's all. Thank you. And now I'm going to conclude what I have discussed with the reporter. I asked whether he used hand to release the ball, and meaning that there's an initial velocity, and he responded that it is just an observation. He did not include that in his experimental data. So I think that's maybe by some misunderstanding. And the second one is the water. Water is the major contribution to the sound according to the sound. But I disagree with that. I think that from my equation up there, the K is actually changing. So I think that this is actually the ball that determines what the sound you hear. And what characters here you say that it is wailing, but you give a multitude of definitions of wailing. So I am not quite know what you are going to talk about the wailing is. And you have in these two pages, you lack notations that need to be confused. And as the AB part, it is insufficient to just simplify that in that way. And that's all. Thank you.
Okay. So question time for the reviewer.
Okay, so both to the reporter and opponent, what do you think the most important parameter of this diagram?
I think would be the water distribution, like the M max right there, and the ball, like the K there.
So what about
I think that is the geometry shape they correspond to the whirling sound.
okay, and to reporter, how do you control the force when you strike the ball? Because from the video, you just strike the ball by hands.
Yes,
So how do you control the force?
and because in these cases the whirling sound is complicated, so at first I'm gonna go to qualify the force I strike it, so I just to see how the whirling is at the different parameter.
Oh, okay. And did you try the different types of the liquid, just like oil and alcohol?
And for the problem statement, it said that when the ball with some water, so I'm not going to change the liquid of the ball.
Okay. And did you think that there will be some energy loss when you strike the ball?
I consider the kinetic energy and potential energy, and the kinetic energy and potential energy can be extended by written, and like this. Sorry. We can see I consider the kinetic energy and the potential energy by the kinetic energy of the ball and sorry, and
And how about you?
Like-
Do you think that there's any energy loss when the recorder?
Yeah, I think when you strike the ball, the input energy is the force you strike it. Then you will transfer it to the water, that like the water vibrates and the ball will also vibrate, and the sound also vibrates, and the water and the ball will also have some friction on it.
Okay.
So,
Time is up.
and I add the point.
Time is up.
Sorry.
So please start.
So how everyone, I'm review of this topic and I'm reviewing Tingwen and I'm from Tinghua and my school is National Shanghai Senior High School. And today I'm reviewing the topic of 15 volleyball. And this is problem statement. When you strike the side of metal ball containing some water, you can hear a characteristic sound. The sound changes when the water in the ball is moving. Explain and investigate the phenomena. And the reporter main focus on the definition of volume and the factors of sound change. And their experience said that they use both hammer and water to fill in the ball. And their result, the varying water shakers, oscillation frequency, and strike position. And strike position doesn't affect the termination of frequency. And for pros and cons for a recorder, we think that the recorder has lots of parameters, has conducted lots of experiments to want to know about this phenomenon. The content, he didn't finish the presentation within the limit time, and the chart do not clearly explain the information. And for the opponent, the shot as starting goes in opponent reasoning. But the concept unable to effectively counter the reporter's viewpoint, and to focus on the formula. And about discussion, the opponent asked about the reporter. The ball vibrates only about the air and the sound. The reporter says yes, but we feel that you have to consider more theory. And next, the opponent asked about is the standing wave affected by the ball. The reporter didn't respond clearly, but we agree with the opponent's opinion. And the next question, opponent asked about how to measure the angle. The reporter respond with pull the ball with pen, and we think that you should measure it in a clean way. And about the next question, here is the opponent will ask about the reporter. Here is the definition of the wording. The reporter respond with the frequency we hear, and we agree about the reporter's opinion. I want to ask about reporter. Without water can have wind sound. Reporter can understand, and we think that without water it can't have the wind sound.
Okay, time is up. So the reporter, please make the concluding remark.
Okay, so for the conclusion and the remark, and I define the welding sound, which is the oscillation of the frequency. Also, I do the experiment and to fit the theory, and I got the theory from simple to complicated, and I use the energy and the height of the and the shape of the and the geometry shape of the ball and the water to be considered the welding sound, and the vibration mode, and I also do the vibration mode connected to the frequency. And since when you strike the ball and the energy, when you strike the ball, the kinetic energy was too big and it will influence the ball's geometry shape, and so we can know that the kinetic energy and the energy will be considered it. And when we hear the sound, the frequency is by the vibration mode, and the frequency can correspond to the motor 4 vibration mode. And we consider the background noise from this SFT and consider it and what the water cause and the definition of welding sound and how it will appear in the STFT spectrum. And this is all my concluding.
Okay, so the question time from the children.
Yeah, so this question is for the reporter and your proponent. So, we all agree that wailing sound could be defined as the vibration of the dominant frequency we hear, right? So this vibration sometimes may also have its own frequency. And so, what factors do you think could contribute to this frequency?
So you want to first or okay, I first. You can see that in this equation I provided here. In this, you can separate a ball of water into a finite ball of water into an infinite small pieces of small water, and to represent it in each metric units here. And you have a corresponding K here. So it is the K here that determines the frequency you hear. And when the M here, as the M corresponds to 1K, and when you draw all the graph of the frequency and you combine it together, you will hear that the wailing sound. So the wailing sound is typically depends on the K here.
I think the vibration mode corresponds to the frequency is about the complicated theory about the French theory. It uses the vibration mode and to correspond it to the frequency by using the Young's modulus and the radius of the ball and the density of the ball, and it also the vibration mode corresponds to the frequency by the standing wave, and the standing wave of the number of standing wave and the amount of standing wave and is presented by the n, the ratio among the ball of a ring, the standing wave it has.
Okay. Yeah. So Professor Huang.
Two questions. First one is for the opponent. So looks like you know a lot about electricity. I think I said so.
Yeah,
can you
because
elaborate?
in the opponent's assumption, he assumed it
Can I
to.
Can I elaborate my question?
Oh, sorry.
Yeah. So these are from the electricity textbook. So can you elaborate what's n here and what do you mean by eigenvalue here?
Okay.
Say the big words.
Because the time is limited, I can
Yeah,
direct it.
just.
So the first part is that we had water inside the ball, and in this finite area, we separate this water into an infinite small pieces of ball. Like here I have a finite script, and I can distribute it into infinite small amount of these things. You know what I mean? And this is called a finite element method. I think so. So here is the mass. This M represents the distribution of the mass inside the water, and this is the acceleration of the mass. Well, equals to the K here represents the K he used in his theory where omega 2 is mk, and x is the displacement. So if we solve this equation, we can have a general solution where the x is U, E, I, omega, T. And we substitute this back here. We can get that, did I need to do the calculation? No, so we will have the eigenvector of U.
That's good enough. I think you know a little bit about solving the differential equation. Okay. So can I ask another question?
Yeah.
So the question is for three teams.
But short question.
So the problem is that the water in the bowl is moving, right? So from your argument or your presentation, it looks like you just think that the shape at any instant is crucial in determining the frequency.
Yeah.
But let me just finish. Time is short. But water is moving means water has some velocity field, right? Actually, it's not static. Yeah. So I want to comment, just give you intuition. So how much is the inference of the moving water instead of just you just look at the shape, right?
In my opinion, I use the console to simulate in the condition of the quantity-steady mode, and it means that I qualify the condition of the degree of the water and the ground, and I do a lot of the degree and get the picture of it and do the animation, and we can know the vibration mode in this condition, and I also do the okay.
Just short.
Shortly.
about
Yeah.
this question?
So three of them, three teams.
So, reviewer.
Yeah.
Oh, okay.
Please
Nice.
only
Reviewer.
use few sentences, not too much.
The velocity will affect the mass distribution in the M, so that it will correspond to 1K, and you will get a 1 frequency. So if you get a lot of time, so you get a lot of time, the mass distribution of that time. So you can get different K and you can get different frequencies. So you graph it and you can know the frequency.
Okay.
And we agree with Apollo's opinion.
Yeah. So scoring time. The score for the reporter. Six, 5, 7, 6, 7. The score for the opponent. 8, 6, 7, 6, 7. The score for the reviewer. 5, 5, 5, 5, 5. Yeah, 4, 5. Okay. So let's take 15 minutes of break.